Hello. So today we will talk about linked lists in our course data structures. A linked list is basically a data structure that allows efficient data management. It is similar to arrays in the sense that we will store data, but there are fundamental differences. Uh, Basically, the array, the traditional data structure that we are familiar with, it allocates a block of memory at once, and it arranges its data as a set of consecutive blocks in that memory block. In a linked list, the strategy is different. Every element will be a different memory, will be located at a different memory location, and those memory locations will be linked together through some pointers. Okay, so yeah, basically a linked list is made of nodes that are pointing to each other, and again the locations of these nodes in the memory is totally arbitrary. In an array it is not arbitrary. You have this arbitrary block of memory, but once you get that block, all the content is contiguous in an array. So you can go to the next item by just doing some arithmetic, like adding some offset. But in a linked list you don't have any offset. You need to follow your next pointers. Just like here, I have this head of my linked list pointing to the first element, first node consisting of the data part as well as the pointer part. So the pointer part points to the next node, which points to another node, and the final node, the last node, will point the next of the final node will point to the null, which we represent with this ground symbol for some reason. Okay, so this would be the first node, and this would be the last node. These are the intermediate nodes, and head is the access of the programmer to this linked list. So he or she cannot access the middle node in one shot. He or she always starts with the head, and then she needs to advance these pointers to come to a certain location. So if your linked list is empty, then basically the head, which always exists, it has the value of null. So it just looks like this. There is nothing that it points to. So it exists conceptually, but physically it doesn't really exist because it has the content of null, which is 0. Now I will do some nodes to make this useful and interesting. And as I mentioned, every node will be consisting of at least 2 fields, which are data and pointer. This data part can be huge, like even megabytes. So there is no bound here really. But if you are storing numbers, then the data part will be 32 bits, which is 4 bytes, right? So, but again, you can be storing an object of a class that has huge content in it. Okay, then this data part will be huge. But one thing we are sure of is the small size of this pointer. Pointer is basically an 32-bit integer pointing to the next memory address, right? So this is a small location, small size thing within my node, so it is not a big deal to store this pointer actually. So the thing that I mentioned in the very beginning can be visualized here. In a linked list, nodes are not necessarily contiguous, okay? Contiguous in memory. Each node is allocated with a different new call. So as you require them, you create them, which is the cool part of a linked list. But in an array, you get the allocation in one shot with some amount, and it is the problem. What is the amount? You will probably overshoot. It is better than undershooting. But when you overshoot, you will be wasting that unused part of your memory. Yeah, so that is the difference, and the differences are continuing actually. So array is also useful, and the most prominent advantage of an array is this random access thing. So since you have this access to this beginning of the array, so you know this first element, and then to go to the seventh element or something, you just add 7 times the offset. So you start. So your offset will be 7. You add it to your initial address, which you know. So you can do random access easily. But with a linked list, to go to the 7th node, you need to do 7 iterations. You need to call next, not call, but you need to do p.next, p.next, p.next 7 times. Or in the general case, n times. So random access will be on, worst case time, in a linked list, whereas it is just o1 in an array. So this is a huge advantage of array. But also a slight advantage is there is no need to store pointers, but as I mentioned, it is just a tiny memory. The pointer is, so it's not a huge advantage. Disadvantage of an array is the fixed size. So once you start with an array, you cannot grow it without any cost. You can, of course, but then if you double this size, then basically you have a new array of 2n size, then you need to transfer the existing n arrays there. So it means that you need an on time work to double your array size or to reduce your array size. So this is a disadvantage. Also, what is the initial fixed number, right? We don't really know it in advance. So we generally have dynamic situation going on. But if you are implementing a dictionary like Oxford English Language Dictionary, then the size is more or less fixed, right? So you don't really add new items every day to that dictionary. Then array can be okay. So depending on your problem, really. And also, if you want to insert something to the middle, then like if I want to insert something here, then I need to shift all the other guys one right, so including this one, because now a new guy comes here, so this block will be shifted one right, which will take on cost. Similarly for deletion, I need shifts. So linked list doesn't suffer from that intermediate deletion or intermediate insertion, as I will show you. To insert something between this and this, for instance, you create that node and then you set the pointer of this to here and the next of this to here, and you kill this pointer. So it is as simple as that. It will take just one time, as we will see later. You don't really need to shift anything. Also, another advantage of a linked list is the dynamic size of it, which means that it can grow and shrink as needed, meaning that if I want to add something, there is no fixed size. I can just add it to the end or to the middle, as I did here. Similarly for deletion, I can just delete it. And there is no wasted memory, actually. Everything that is in your life will be in your linked list, not more, not less. But the main disadvantage is this direct access problem, random access problem. You need to follow pointers, which would take on time, as I discussed in the beginning. But with an array, it is just one shot. Okay, so if we wrap it up, in general, use a linked list if the number of elements that will be stored cannot be predicted at compile time, so before the execution time, which is mostly the case in my experience. So it is one rule. The other thing, if you are inserting to the middle, not exactly the middle, but you get my point, like not to the beginning, okay, to anywhere else, or deleting from anywhere else, then array is not so good. But linked list is very good. And also, if you are less likely to do random accesses, then you will not get hurt by that problem of linked list. So linked list is still a good option. Let's do some coding then. I need to start with a class called node, which represents the element, the data, as well as a pointer to another node. Okay, so next is a pointer to a node. And again, I am doing template programming here from C++, as we learned. So if the I bind the variable during the execution time here. If I set it to integer, then the element will be integer. So you will replace all t's with int. And this node, so let's also add a constructor here which sets the default value of element to the default value of that type. For integer it is 0, and which sets the default value of next to n, sorry, which sets next equal to n. Remember, this is not syntax of C++. And what is n? If you don't provide anything, n will be null. If you provide something, n will be that thing. So that is the node class. I also need a separate class called list or linked list. We go with list here. So this list is the gate to the developer, to your main function actually. And from this list I can access to the nodes. In particular, I have this head node that lets me access to the first node if I have that node in my linked list. So head will be pointing to that node as I fill this up, and then this will point to another node if it exists through the next pointer of this node. So initially head is null. So initially I am talking about an empty linked list. So I have this head conceptually, and head is equal to null, meaning that head, so sorry, not this, but this symbol, ground symbol for null. So let's add some services to this list class, and then you will get better at the linked list stuff. So isEmpty, it is a read-only function. It will not update any member of this class. That's why I will make it constant, but it is not super crucial actually. So isEmpty will probably and will return whether head is null or not. So if head is null, then it will return true. If head is not null, like I have a node with the data of 7, which has a next pointer to a null or to another node, it doesn't really matter. But the thing is, if head is pointing to this, then this 7 or this node is not null, then isEmpty will be false. First, so remember, this is the public part. Head is a private member, so I can't really access to head directly from my main function in a different class or from a different class. So I need a public function called first, which would return head actually. It just makes the reading better. Okay. So whenever I ask for the first element, it will give me this node with number 7 in it. So let's also fill this linked list, I don't know, with 6 here, and let's let this linked list have only 2 elements, 2 nodes. Then the next of this node will be null. Let's do an insertion then. So to your insert function, you expect a pointer p that points to a node after which the insertion will take place. So let me repeat, the programmer must give me these 2 information. Okay, so don't expect everything from me. So the programmer will give me this p pointer. Okay, like it will tell me that do the insertion after p, and in the insertion create this new data value called x. Okay, so it is the order, right? Sorry, first data then pointer. So I just wrote it in reverse order. So this should have been x and this should have been p, but it really doesn't matter. So let's stick with the slides notation here. So what you will do is, I already have this in my life, p, and p dot next is b. So this is already an existing linked list, the upper row here. Then when I want to insert x, I will create a totally different, I will allocate a memory that is in a totally different location, in a totally random location. So I allocate this memory, and then I will put x as the data member of this node, and then I will set the next of this node to the next of p. So this will point here. but this is also not pointing here, so it is kind of weird. My linked list starts from here, it comes to A, and then it goes to B. There's also another thing that I don't have an access, so you make that access by setting p.next. So you cancel this. p.next is not B anymore. p.next is this new node from now on. Okay, so this is going to be insertion to the middle case, and insertion as the first element or to an empty list will be slightly different. So let's analyze it over the code then. So this is what I just described to you. Okay, this is case one, the insertion to a middle-ish point. So I create a new node. Okay, so maybe should we, okay, let's go over here again, or let me just create illustration here. So I create a new node. So I already have this linked list coming up to this point. So p pointer points to this node. So this has a value of 7 in it, and this, the next of this node has already been set before because I already have a linked list. So let's let that have value 6. So I want to insert after p. So new, remember C++ allocates a new memory, and into that memory put data. So let's insert 8. So data is 8. I put it here. And then remember the node constructor. This is the data part and this is the next. So what is the next of this node? So the next of this node is going to be p.next, which is this. p.next is 6. So basically I set it like this. So with the first line here, I obtained this configuration. But it is not over because p.next is 6. I want to cancel it and I want to replace it with this new node. So p.next is this new node that I have been pointing through something called new node. This is it actually. But if you are inserting to the to an empty list, then head is pointing, head is null. Okay. So what you do is you create a new node, okay, with data 8 in it, and 8.next is going to be equal to head. So initially head was null, so this is pointing to a null thing, and difference is here, head was pointing to a null before. I don't want it to do that anymore. I want head to point to this node. So here is your linked list with one element in it. So starting from an empty list, I have obtained this, but it doesn't have to be empty. You may already have a linked list. So let's go with this. I have this linked list, right? Just created before, 7, 8, 6. Now I want to insert as the first element to this linked list. Then I will call this function with head. So remember head is pointing here. So I create this new node. So let's insert 4. No, I create this new node called 4. Remember I am inserting to the as the first element. So 4 is created. Now 4 is this data. 4.next is head. So 4.next, head was pointing to here. So this is the new 4.next is 7. And finally head must be updated. Head will point to this 4 now. So here is my insertion to the first node. So my linked list is now 4, 7, 8, 6. And since this is the last node, there must be a null here. Now you can see some complication here. It is not that complicated, but at least there are cases. So I have separate case when I'm inserting as the first element, because then head needs to be updated. But for other cases, I have this case. But now I will get rid of 2 cases. I will use something called a dummy head to make this insertion a single or 2 lines of code. So it is just an efficiency issue actually. You can still go with this, but trust me, this would be even better. It will also help in the deletion. So what we will do is, remember I have this head pointing to the first node, but now I will create a dummy head, okay, just like head. It points to a node that always exists in memory with a weird dummy content called X. Okay, so I really don't care about this content. What I care is this is not null. So dummy head is never going to be equal to null. It will always be this. So then you can also consider this as a zeroth node. Okay, it will, if it will make you more comfortable. So this will be your zeroth node, and the next of zeroth will be the first node. So this is the actual data, non-dummy data. So if we have this in our lives, then an empty list will look like this. Dummy will never be null, but dummy.next will be null. So first will be null. Zeroth is never going to be equal to null. Then the insertion would look like this. Be careful, it is just going to be 2 lines of code. There is no cases, because so this is just like the before case. If you are trying to do some insertion to a middle, let's remember 6. I have done this before. 7, I think, with different values. So dummy head is somewhere here, dh. It points to something that always exists, okay, it's a weird content like X, and this points to maybe node 3, and this points to 6. So if I want to insert something like to the middle, like 8 here, I just go with then P would be this, right? Then 8, I create this new node with 8, and new node dot next will be P dot next, which is 7, and finally P dot next will be 8. So I am golden. There is nothing difference. Difference is in the insertion as the first item. So let's try to insert 2 as the first node. I will do the same thing, but I will now send here the dummy head, which is never null, so there is no segmentation fault danger here. So what happens? Create the new node with value 2, and P is dummy head. So dummy head dot next is 3, which is the first element. So the next of 2 will be that, which is this, and dummy head dot next is not going to be equal to 3, but I will update it to 2. See, the same code does the first point insertion, first node insertion, as well as intermediate node insertion. That is the trick, actually. Okay, so we will stick with that formation from now on. Again, if you want to zeroth node, you will be getting the dummy head, okay, which will never be null. If you want the first node, it can be null, but it will always work, because dummy head dot next, dummy is never going to be null. I also have the constant version of this function, because isEmpty is a constant function and it calls first, so I need to have this in my life. Let's do more services. Find a data in a given linked list. So do I have a linked list now? So let me it is quite complicated here, so let's redraw it. Basically, remember our formation, dummy head that points to this dummy node that is not null. So let's put some items like 3, 5, and also 4, maybe it's enough, I guess. Then the last node will point, the next of the last will point to null. Basically, you will go like this. Start with the first node. So this is the zeroth node, this is the first node. Okay, P is this. Is P okay? So this is basically saying that while P is not equal to null, right? This is just a shortcut. A cool programmer does it with only one character, while P is okay, or you can also write it like this. If P dot element, which is 3, let's try to find 6. Is it equal to 6? No. Then I advance P. P becomes P dot next. So this is something we will do many times. This is the heart of a linked list. Advancing pointer. P is equal to P dot next. So this is the new P. Now I repeat. 5 is not null. 5 is not equal to 6. So P is equal to P dot next, which is this 4. Again, 4 is not null, but it is not also going to be equal to 6. So P is equal to P dot next. So P becomes null. And while P, so P is null, it is 0, equal to 0. So whenever it is not 0, it continues, but when it's 0, it gets out of the loop, and I return null because I couldn't find it. If I was looking for 4, then at that last iteration, since when P was here, since 4 is equal to 4, I would return this node, and the caller will do something with it. Deletion or removal. Similarly, but in this case it is called remove, I think, not delete. So remove, let's write just rem. The user needs to provide me the value x, only the x, no other pointer. Your task is to find the node that is previous to x, and then you will bypass the node with x. There may be other x's in your life, the same value. You will remove the first occurrence of it. Okay, so as I mentioned, you need to find the previous. So where is the so this is the remove. It expects only one data value, like 7. Then you will call find previous with 7, and you will find that node and then do the bypassing. So let's keep things in motion here, basically. So let's again create a linked list with the dummy head that always exists with a dummy entry, so I won't even draw the box around it. So this is the 0th node. The first node will be, I don't know, 2, then 5, then 4. Okay, so let this be the last guy, so it points here. So let's also keep another node, like let's keep node 22 here, and then let this be the final node. So I want to delete number 4. Okay, so then I need to find the previous node that is previous to 4. So basically I need to find this node that I will call PR for previous. But how do I find it? So start with the 0th node. Okay, why? So here be careful, I don't start with the first node, because of that I might be deleting the first node, right? So I might want to delete number 2. Then the previous of 2 would be the 0th node, and I need to hit it, so I need to consider 0th node as well. That is the trick. So start with the 0th node. Do I have the next of it? Yes, I have a 2 here. So then I won't have any segmentation fault, so go for it. Is 2 equal to 4? No. Then advance the pointer. So P was here, but I didn't like it as the previous node, so this is not P anymore. This will be my new P. Remember, I am going to remove 4. So again, P dot next, it exists. So continue, but it exists with a wrong number. It is 5. I was looking for 4. So don't do return. Advance P. This becomes P. Now P dot next exists. Continue, and it also has the value that is my victim, which is 4. So it exists. So I return this P, and I stop, because this is my task. Find previous to 4, which is 5. So remove gets that 5. Okay, P will be that node called 5. Okay, so this would be P. I don't care the stuff before it. Then let's copy the stuff here. The next would be 4. That will be the victim, and then after 4 there may be other items, like I think 22 I put here, so it really doesn't matter. Then I may be even more items, but let's stop here. So if there is a previous, by the way, if I try to delete 14, which doesn't exist here, then this will never be able to return that previous, so it will return null, because there is nothing preceding 14 in this linked list. Then since p is null, I do nothing, I just quit. But in this case, I luckily have a previous which is called p. Then I will do the bypassing. What is that? I will call this temp. This is just for memory cleaning purposes. Okay, not a big deal. Not very fundamental. But this is the fundamental line. P.next, which is for, I don't like it. I want P.next to be P.next next. Or in other words, temp.next. So let me repeat. P.next is not going to be this. It will be temp.next. Okay, so this is the situation now. This is gone. See, I bypassed this. Actually, at this time it is okay, because your linked list comes here, and from 5 I go to 22, and then I go to other places. But I totally removed 4 from my life. Let's also remove it from my memory for the good memories. So delete temp, and that is why I have kept this pointer. So this is just a memory cleaning issue. Here is a popular interview question. I have seen this in Facebook interviews as well as in Google interviews. So this is a very cool problem. The problem is you need to implement an algorithm that delete a node in the middle. But the catch is the following: given only access to that node. So if you want to delete 7, normally what you do is you find previous 3, then you bypass it, and you get 3, 0, 4. Okay, you are done. But the thing is, you can't call find previous. You are only stuck with 7 here, so you can't look anything to the left of it, and you still want to get rid of 7. So you can pause here or think about it, but I won't do it. I will just proceed. So you will think out of the box actually. Since I have access to this node, I also have an access to p.next, because I don't have p.prev, but I have p.next. So I will copy this value 0 here. Okay, so I will copy 0 here, because I can go there, and then I will bypass this node. So because I am still in this node, and I will make 0.next equal to 4. So basically, I physically removed the other node, but I don't really care, because these are just arbitrary memory locations. The content 0 is preserved, and the content 7 is gone. And see, I haven't looked at anything to the left of 7. So that was the trick. It is also a constant time operation. There is no iteration or advancing. I just do some pointer action. Let me repeat it on a different example. If 3 is the victim, copy the content 4 here, then I have double 4, and I get, so here this part is your original removal, right? Bypass this node, connect 4 here. Basically 3 is gone. Yeah, so that was a cool question in my opinion. Print, so this is an uncool question then, followed by this very basic and stupid action. Print is, you start with the first node, then you print the content, and then advance the pointer. So it is really not that crucial. Some C++ syntax issue happening here. Since it is constant, the constant first function allows print to be constant as well. Okay. Make empty. So I will be using the functions that I have built so far. Basically, while, remember this is inside the linked list class, so while the current linked list isn't empty, just remove the first element, then remove the first over and over again. So dummy head, dummy content, so let's do, I don't know, 3, 6 and 7. So Will it remove from right to left or left to right? This can be the only challenge here. I will remember remove just needs a data value. So go to the first element, remove it. I believe that remove will do the pointer action correctly. So 3 is gone. So this will be the new first element. So then 6 is gone. And also remember, within remove, I call this delete of C++. So memory is also handled. And then remove. This is the new first, remove 7. And then I end up with dummy pointing to null. So this is the empty case. So isEmpty will return true, and I will quit the while loop. And basically this is what destructors are for, right? I need to clean up the memory. So the dummy head is a pointer, so it needs to be deleted, but it is not enough because there has been other pointers, other nodes allocated through new, so, and they are all deleted with make empty, which calls remove, which calls delete in the back scene, behind the scenes. Let's do some operator overloading then. I want to support this service. I want to set L1 equal to L2. So whatever L1 is, I don't care. I will make the content equal to L2. I can do it like this. So let L1 be this. Again, dummy heads point. So this is my access. So L1 is maybe holding even numbers. Okay, 2, 4, blah blah. And L2 is again starts with a dummy content. It holds odd numbers like 1, 3, 5. Their size just don't have to be the same, obviously. So after this statement L1 is equal to L2, I want L1 to be holding odd numbers. Okay, so I start, first of all, is this equal to the right hand side? So maybe user is stupid enough to call this L1 equal to L1. Okay, set L1 to L1, then right hand side is L1, this is currently L1, they are equal, so do nothing because L1 is already L1. Otherwise I am in this statement, they are right hand side, L2 is different, make L1 empty. Remember, this is the call within the L1, so everything that I call without any preceding dot will be applied to the L1. So make L1 empty. Okay, so 2 and 4 are gone forever. So this and the dummy head dot next will be null. So it is what make empty does. I lost all that content in one shot. I don't really care. Now start with the first node of the L2 because it is the real content, and start with the zeroth node of L1 because there is at this time no first node anyway. So start with the zeroth node. So while I have content in L2, insert that content after the P. So P is this. So insert it after X. So let me draw it clearly. This is L1. So this is X. Initial P is this. So insert 1 after X. So now this is L1. X and 1. Now do the advance. So P was this, advance P here. And R was this, advance R here. And repeat. Is R okay? Yes, 3 is an okay value, not null. So insert 3 after P. So I will make it like this. And advance pointers, P is now this, and R is one more shot, like R is this. Again, R is not null. Insert 5 after P, and I will believe that insert will work because I have implemented it previously. So 5 comes here. So this is 5, obviously. P is equal to P dot next, and R is equal to R dot next. So R is null. Be careful. And so while R is okay, not null, it continues. But since R is null, I need to say goodbye. So this is over, and return this, which is the new L1. So I also return L1 because maybe there are concatenations here, like let me do it from here, L2 equal to L3 maybe. I want to support this action, so L2 will be equal to L3 and it will be returned, and L3 will be updating L1 now, stuff like this. Okay, and so copy constructor, again we have studied this when discussing C++. It is basically a constructor that expects another list, which is the copy constructor, so it expects this argument of type list, and it will be using this assignment operator that I have just implemented, basically. Let's test our linked list class now. Here is the template programming happening. Linked list of type T. I will set that type to integer. Okay. So insert number 0 after the 0th element. So this always exists. Be careful. So this is the 0th element. Okay. It is the 0th element. So insert 0 after 0th. Basically, I end up with this linked list. Then what is happening? P is this, because list dot first, remember this is 0th, so this is first fr is it? Okay, fr. Now I will insert the next 10 integers after P. Okay, so 1 comes after P, so basically I have this 1, then T becomes this. Okay, so I will be inserting the 2 after P, so this will be in ascending order, 2, 3, all the way up to 10. Okay, so quick question here. What if I want a descending order? So can I obtain this with a little trick? So I want my linked list to be like this, 10, and then next is 9. So when I'm writing, think about it. Next is 8, and then all the way up to 0. So is it possible that I can obtain this? I believe you thought of it, and hopefully you say that yes, by just replacing this with the 0th node. Be careful, it's a nice practice here. Of course this is list.0th, but the thing is the following: I will not be inserting the next after P. Okay, I will be always inserting after the 0th node. So what will happen is, this is the 0th node. First 0 comes, it doesn't really matter, I insert it after the 0th node. Then 1 comes, I insert it after the 0th node. So it becomes like this, and it will, insertion sets the pointers. So this is the situation. Then 2 comes, but I insert 2 after the 0. So this part is fixed, it is not P, so you don't really have to do this line. Then 2 after the 0, so I have 2 created, 0 dot next becomes 2, and 2 dot next becomes the old 0 dot next, so it is going to be like this. So C210, and if you extend this idea, it will be 10, 9, 8, blah blah 210. Okay, so it was a good practice for you. Then I will be basically removing all the even members. Okay, and then I will be using this assignment operator explicitly, or yeah, explicitly, and then I print stuff, and then I make something empty, so it is not really that crucial after this point. The same stuff is going on here. I will do some variations on this single linked list. So far I haven't used this term single linked list, because there's a single pointer called next, and by default when I say a linked list, I refer to this one actually. But there is a double linked list variation where I also have the previous pointer in addition to the next pointer. There's also a circular linked list. Remember, in the regular linked list, the last node points to null, but in the circular case, instead of pointing to null, it will point to the first item. So I have the circle effect, and I can also combine doubly and circular linked lists. So we already have a figure. So circular linked list is useful if you are implementing a turn-based game, like Risk, for instance, because this player, after the last player, the turn will come to the first player, so it may make sense to switch between players. And just I described, the next of the last will be pointing to the first node. Double linked list, so I already have this next ones. Now with every node, so take this node B, it has a next of C. Now I will also keep the previous pointer, and it will be useful when you want to do some action in backward order. And disadvantage is now I am doubling the pointer size, but as I mentioned in the beginning, the pointer size is just a 32-bit thing, so it is really not big of a deal. But so let's do more on this double linked list. So it is more powerful than a regular linked list because I am supporting back movement easily. So if I want to delete something from a double linked list, so let this be remember the same idea, remove or delete. It expects a value to be deleted, the first occurrence of it. So I will be deleting value 7, so this has the value 7. So I call this, I find this node. Okay, so this is the node to be deleted. So what we will do is the following. I call it the old node. So the previous of the old node is this node, okay? And previous.next, which is this black pointer, it is not valid anymore because this will be gone forever. So I put a cross here, and it will now be pointing on old.next. So I create this blue arrow with this statement, done. I am not done though. Now old.next is this, and the prev of it is this black node. I don't want it to be in action anymore. I want that prev to be equal to old.prev. So I will activate this blue arrow now. And finally, I get rid of this memory, old node, so all this data goes away from my memory as well as this little pointers. For the insertion, again, user must give me this pointer after which the insertion will take place, so I have access to the current. I create, so new node, I create a new memory, this rectangle, I put X in it, okay, and the next of it, I will set it later, so it is just now. So new.prev, I am setting this black thing, is going to be equal to current. It makes sense. New.next, which is this black pointer, is going to be equal to current.next, which is this node. Okay, makes total sense. Then I am not over. New.prev, so this thing, .next. So it was this node. I cross it over. It will now be equal to the new node. So I activate the blue pointer. And similarly, new.next, so this guy, .prev is not valid anymore. I will overwrite it with the new node. So I will activate this blue arrow. Okay, so it is really not that hard to implement a double linked list. So prev pointer of the dummy head points to the last node if you want a circular double linked list, just like this. Okay, prev. Sorry, prev of the last node will point to the dummy node, and so on. And from now on, I will solve cool problems, in my opinion, that requires linked lists. So these are like samples from, again, interview questions, just like the one I have done before, the removal from the middle thing. So if there are even more, so I didn't collect them from this address, but I discovered this Stanford course site that has other examples for your practice. So these are my selections. Find the nth to last element with one for loop. So here one is important. I can always do one for loop to find the size of this linked list, and then given n, I will just go last minus n items. But then I will be doing one plus more loop. To do it with one loop, I will start 2 pointers from the beginning, and I will let A move n times, B is still fixed, and then they will move together. So what it means is when A is A finishes, B advances to the end, to the last element. It is the idea. Print a linked list in reverse order. One obvious answer is to update the linked list, like reverse the directions here, okay? And actually I will show how to do it later. And then print, so this will be the new head since it is reversed. Then print 3, next 2, next 1. But I will do it without updating the linked list using a recursion here. This is my input, first node, second node, third node. It calls, so let's go over the recursion here. Since the first node is not null, it means I have a linked list in my hand. Call recursively the same function using next of the first node, so using this part, which is 2, 3. This is not null, so call recurse using the next of 2, which is 3, which is not null, so recurse with the next of 3, which is null. Now the interesting action begins. The new call begins with null, and basically it is null, so I return. I do nothing because I don't have anything in my hand. But when I come back, so I am rolling back the recursion, I was here with 3, so it has finished its recursive part, which led to this null thing. Then I will print this linked list's first element, so it is already a 1 element linked list, so I will print 3. So it is also done. Now I am at this rollback, 2, 3. So I paid my debt by the previous recursions about 3 and null. So 2, 3, I will print the first element of it, which is 2. Then done. Then come back to this recursive call. Recursive part is over. Go to the other remaining part, which will print the first element of this 1, 2, 3 linked list. So it will print 1. So 3, 2, 1 is printed. Obviously, you can also use a stack to put all the content to a stack and then read it from the stack using pops, but we haven't covered stacks yet. So this recursion is neat in my opinion. But now I will show you how to reverse a linked list. So I will update the linked list. So if this is my input, like head, the first node is 30, then 25, then 20, and let's also write one more, 15. So the idea, you can visualize what I will do as follows. I will just reverse these directions. So basically this will be reversed, this direction will be reversed, this arrow will be reversed, okay, 15 will be reversed. So if you, and let's finish it as 15. So read this linked list, 15, 20, 25. So this is what I want, right? 15, 20, 25, etc. So basically I will be updating these arrow directions. I will be negating them. Let's see how I do it. Start with 3 pointers, current, prev, next. So initially current is the head, which points to the first node. So I am not using a dummy head here. Current is this. Next of it will be current.next, so this will be the next, and the prev is initially null, which makes sense. So see how it will do the negation here. Current.next, be careful, is going to right. The direction is from left to right. It will be whatever prev node is. So basically it will be this, okay, because prev node is this null. So current.next is null. Then what happens? Then I shift everything to right one step. So prev node becomes, so this is prev, this is current, and in the next iteration, next node will be this. Now it will be even more clear. Current, so current.next, be careful, this direction, so 25.next was 20, but I want it to be 30, so I will do this. 25.next will be this. See, I negated this direction with that trick. Then I shift everything to right one step. So this will be prev because of this line. This will be current, and this will be next. Now let's do it again. This is current, be careful. So next is, okay, I set it. So current.next, 20.next is 15 in the original case, but now I want it to be 25. So in other words, I am basically doing this thing. 20.next is 25. So this is just killed. There is no arrow here now. And then I do the shifting again. So prev becomes this, current becomes this, and next becomes this. Do it again. Current.next is 20, is the previous, which is 20. Shift again, so this becomes P, this becomes current, and this becomes next. Do the reversing. Current.next, so this is the crucial line here, is equal to 15. So I do it like this, but I won't draw it like this. I will draw it this way. 10.next is 15. Advance one more time, so this would be the prev, this would be the current node, and now the next node will be null. Okay, but I still have some work to do here. Current.next is going to be 10, so 5.next is going to be previous, which is 10. Okay, so it is also done, but now be careful. There is some more action to do. So shift again. This is P, this is current, and this is next. So it is still null. So now this is also required. Now I have created this linked list, which is okay, but there is no head of it. Actually, there is a head which still points to 30, but it doesn't make any sense because 30 is in the very end now. So in the end, I need to set head equal to this node, and be careful, I already pointed this node using the P. It is because I just shifted one by one, so P still has that information. So set head equal to P, which is 5. So now see it from right to left, head 5, 10, 15, blah blah, and read it like the traditional way, head 5, 10, 15, blah blah. So this is a useful, a nice practice that helps you play with pointers to reverse the linked list. I will show you more examples like merging two linked lists. So this is, I think, L1, obviously this is L2, at alternate positions. Meaning what? 5 from here, 3 from here, 10, 6. Okay, so I am kind of zigzagging. So I will call this alternate with function. So from main, I will do it like L1 dot alternate with AW L2. Okay. So in the end, I will be updating L1 with this content from L2. So there are many ways to do this, but let's stick with the one that is given here. So what is happening here? You start with the first node called P here. Now to keep things as simple as possible, this function goes like this. Since P is okay, so P exists, it means that after P, so remember the notation of insert, some data to be inserted after P. Okay, so after 5, I will insert some data, and that data will be the first element of L2. So it is going to be insert the first element 3 after P. Okay, so insertion will also set this pointer automatically for you and kill this out for you automatically. Now the cool part begins. Since I will repeat the pattern, I need to get rid of this. So L2 dot remove the first element. So I will remove 3 from here. There may be other 3s here, but I don't care because I know that it will remove the first occurrence of 3. So L2 is now like this. Again, the remove function will arrange the pointers for you as we have discussed before. And now be careful, P equal to P dot next dot next. Why? Because I want to make the next insertion, which is 6, after 10, but P is at 5. So P dot next will bring me here. Not satisfactory, because then I will do 5 3 6. I don't want it. I want another next. P dot next dot next. So P is equal to P dot next dot next. So P comes all the way to this 10, and then I repeat the pattern. 10 dot next. So insert this value 6, okay, which I borrowed using L2 dot first dot element after P, after 10. So it does that insertion for you, and the pattern repeats. Nice. So this takes O(n) time, right? I just moved through all elements. Split, another problem. Split a linked list L into L1 and L2 such that new linked lists will contain alternate nodes. Okay, so odd indices will be at L1, and the even indices will be at L2. So basically I am going to do a call by reference here. I already have the linked list in my life, like this linked list. L is this. Okay, so let's write it here. L is equal to this. 1 2 1 2 1. For some reason it doesn't have an interesting content. So from this I will create two new lists, again using call by reference. That's why I won't be returning L1 and L2. It is just a detail. So how to fill them? They are initially empty. Okay, so start with the first element, P. Okay, since P exists, I insert this P to L1, and be careful, A is responsible for L1 and B is responsible for L2. So insert number 1 after the 0th element. So initially L1 is like this, right? It always has this dummy pointer, the 0th element, and initially it is like this. The first element is null, it is empty. So this is the 0th element, and this is the first element, which is null. But now insert number 1, so this is 1, after 0th, after this. So I will be inserting 1 after this, and it will set the pointers like this. So okay, 1 and then null. So this is the new first for L1. And I advanced A. Why do I do it? Because I will grow it like to the right of it. I will not add the new content after X. I will add it after this thing. So I will call this, not P, sorry. I will call this the new A. So A was this before, now A is this. But I advance P because I am done with this one. So this is P. If P exists, it may not exist if I am towards the end. Then I do the same for L2. So I will insert 2 to the beginning of L2, and then I advance P. So P is this now, and I repeat basically. And the only trick here is I will insert the next item, which is 1 after this one, because P is this. So I create this node and I insert it after this one, and the next of it will be the null. So see what just happened. L1 is dummy 1 1. So dummy 1 1. This is this one, and this is this one. So sorry about the repetition of the content, but this is the example. And do another problem. Add two numbers represented by a linked list. So 1007 plus 93, 7 plus 3 plus 0 plus 9. There is some carry, 0 plus 0, 1 and 1. So this will be 100 and 100, 1000 and 100. But to do it clearly, to see things clearly, basically I need to pad this with the zeros here, just to align everything, okay? So let's just begin with that. Whichever the closest, the shorter one, so in this case L2 is the shorter, so L2 dot length is smaller than L1, then I will pad L2 with this many amount of zeros. So I will implement this function pad. It will pad, it will, so given, basically let's do this function. The linked list is like 9 and 3, right? And the pad is called with 2 because I need 2. The difference is 4 minus 2, 2. So I need to insert zeros, but I will insert them after the 0th element. That is the tricky part, because So there is this zeroth element that points to here, but I will insert 0 after the zeroth, so it becomes like this. But I will do it twice because of n equal to 2 after the zeroth. So I will do it like this. So now I obtain this 0093. Okay. And by the way, I have used a length function here, which doesn't exist in the natural basic linked list implementation. So you also need to implement this. I think it is forgotten here. Yeah, it is forgotten. So if you try to implement a length function, basically, so let's convert something that already exists to a length function. So I don't want to write. There was a print, I think, at some point. I made fun of it. So okay, print. So I can make this a length function. Okay, length. It will return integer then, int. So how do I make it return the length of a linked list? I start with the first element. Okay. So the number to be returned is int s for size, because I don't like the letter L. So initially s is 0. So while p exists, I advance p and I also advance s plus plus. Okay, and then return s. Return s. So you always need to double check because of this zeroth and first issue. Sometimes you overshoot, so I think I am overshooting here. So starting with the first element, so this should have been 1, right? Because I already have the first element. S is 1. Sorry. If I have the first element, sorry, S0 is okay here. If I have the first element, then s plus plus s becomes 1 and I advance p, right? If I have the second element, s becomes 2, etc. If I don't even have the first element, then s is 0. So assume that I am given an empty linked list. Then p would be null, so I won't be entering here. So I will be returning 0, which makes sense. So okay, we have implemented the length function. So let's come back here. Where were we? Okay, so far so good. So I did the padding. Now I have the stuff ready, aligned, not ready. So I will proceed, but I will do like this. I will start with the last node. I can go there. I will add 7 plus 3, and there will be carries or whatever. But then the thing is, topologically, I need to go back. So I need a previous pointer. Okay, so I need to convert this to a double linked list. So to do that, I need to arrange the previous pointer. So let's do it using the setPrevs function. So how do I do it? Start with the first node. Okay, PR previous is null initially. So first node exists. P.prev. So this .prev is null because PR is that. But now I will advance it. PR is this for the next iteration, and P is this. So now this is the P. Now be careful. P.prev, so 0.prev is going to be equal to PR, which is this. So I have just set this pointer. Okay. And then I advance. So PR becomes this for the third item, and P becomes this, and I repeat. So this function sets the previous pointers as well for you. Okay, so we are towards the end. I think the remaining issue is about mathematical stuff. Like now come to the last node. So I begin with the first node. This is a linked list. I need to begin with the head. So P will be responsible for this list and Q will be responsible for the second list. So I will move P here. I can do it with this while loop, right? P starts with the here. P.next exists, so I advance P this P dot next exists, P is this. P dot next exists, P is this. Now be careful, P dot next doesn't exist. So while stops, P is here. Similarly, Q is here. Now I have this carry initially 0, C is 0. I will create a new linked list as my output. So the value to be inserted to the new linked list will be the following: 7 plus 3, which is P dot element plus Q dot element, plus the carry, which is initially 0, right? So I have value equal to 10. If value is less than 10, then there won't be any carry. That's why I will separate this into two parts. So carry will still be 0, but I will be inserting this 10 after the zeroed item. So this will be the resulting list, L3 or R, whatever. After the zeroed element of it, I will be inserting the value V, which is not less than 10. In this case, it is 10. So I need to take the mod of it. Basically, in the first iteration, I will be in the else part. 7 plus 3 is 10. So carry is 1 for the next iteration, okay? But 10 mod 10 is 0. So I will be inserting value 0 here. Just arithmetic after the zeroed node. So this will be the current resulting linked list. Now I will do advancement in the reverse order. P is equal to P dot prev. So this is the P and this is the Q. I am using the prev pointers. And I repeat, 0 plus 9 plus carry, which is 1. So 0, 9, 1. It is 10. So I am again in the else part. 10 mod 10 is 0. So I will be inserting this after the 0. Be careful. I will grow it from right to left, just the way I want. So I will insert it here, 0. Now P becomes this and Q becomes this. And carry is 1. So here P plus Q, 0 plus 0, and carry is 1, 0, 0, 1. The answer is 1 total. And now I am in this if part because 1 is less than 10. So I will insert it after the x. So far, let me write it clearly. The linked list is like this: x dot next is 0 and 0 dot next is 0. I will insert 1 after x. So I will put 1 here, and then insertion will set this pointer for you automatically. So this is the linked list. 100 part is here, and there is no carry because I was in the if part. Okay, so in the last iteration, finally, P becomes the first node and Q becomes the first node here. And if we do the additions, we will be ending up with 1 plus 0 plus carry 0, which is 1, right? So you will also put that, create a new value called 1 and insert that 1. So I will be executing this statement. Insert that 1 after the zeroed element, which is this. So x 1, and it connects to the existing 1. So I have 1, 1, 0, 0 in my hand. And there may still be remaining a carry in the end. So then what does it mean? You need to put an additional 1 to the very beginning. So you will be inserting the value 1 after the zeroed element. Yes, and this is the final question. What is this? I show you before and after, and I want you to write the code that makes that effect. So here, A, if you say A, you will be hitting the first value. After is this. So B becomes this. So let's first do B. B, when I say B, I get this node because B is the head. It points to the first node. Again, there is no dummy node here. B dot next, so it will set this, right? 3 dot next, because B is 3. 3 dot next is normally null, but I want it to be 2, which I can get from here. What is that? B dot, so I will get it like this: B dot next is going to be equal to a dot next, right? Because with only a, I will get 1 and 2. I don't want to get 1. I only want to get 2. And 2 comes with this, everything comes with this null ending automatically. So I don't even have to say it. So with this line, this thing happens. And next, I am not done yet. I want to trim a, to trim the first linked list. So what is going to happen? A dot next is null, right? A dot next is normally equal to 2, but I don't want it. I want a, so 1 dot next to be null. So I set it to null explicitly, which is the answer here. Let's do the other one. Actually, it is similar, I guess. So a dot next, a dot next will be, I will need to get b dot next dot next, bnn, b dot next dot next, and 3 comes with its ending, null ending automatically. So I have this now, and now I can get rid of the last element here. How can I do it? Using b dot next, b dot next, so b dot next is null, because it is normally 3. I want it to be null. So something like this, it is the true answer actually. Yeah. And so it is the end. There may be other examples obviously, but these are the ones that I personally like, and some of them were actual interview questions from big companies. So I hope that it makes it clear for you. The linked list topic is clear now. Yeah, thanks.